Okay, so we're going to start looking at module number 2. So module number 2, we're going to look at our learning plan first. And our learning plan identifies chapter 2 as the chapter we're going to be looking at. So if you wanted to follow along in the ebook, you would go to chapter 2 in there, and you can just click on the link to the ebook and launch it. And we're going to be looking at a couple of the sections here. Now, we are going to have this connect assignment associated, another connect assignment associated with module 2, as well as practice problems, just like last time, and application problems. Now, if you happen to be in the room, I do have the practice problems and the application problems up here. So if you wanted to grab those, feel free to grab one of each. But if you are not in the room and you're on Canvas, you're going to find the practice problems and the application problems right here. So I'm going to click on our practice problems. And this would be then the PDF. And these are going to be the sample problems, the concept applications, and such that are going to be the examples as we go from section to section. So these are going to be the ones that we'll be doing together in class that then you will have to hand in or take screenshots or snapshots of, and then you're going to upload those to the practice problems. Again, remember, those are basically just kind of the proof that you've been following along, and it gives you that experience with the problems before you do the application problems. So the application problems are here. These are going to be throughout the chapter. So you're going to notice that there's a couple that start on pages 26 and 27. Then we move to 35, 36, and then we have a couple on 61. So how the chapter is structured is they'll kind of talk about some concepts. They'll do some examples during that time. Those are our practice problems. And then at the end of that section, they'll have problems that are going to be associated with that. So if you have any questions or are wondering how to do it, immediately before those pages are going to give you some insights. And then they'll talk about some more concepts, and then do that very same thing, have another section of problems. So that's why I added the page number. It's that they're not all at the end of the chapter. Okay, so with that, what I'm going to do is I do have my physical book here. So I'm going to go underneath my camera. Okay. And we're going to kind of look at this kind of section by section, if you would. Oopsie, zoom out. And then we'll stop along the way to either kind of explain things or to do an example problem. All right. This is good. Okay. So chapter 2 officially starts, if you would, on page 18. Okay. Gosh, that's really hard to see, isn't it? For you guys, they've got a light right above my camera, and there's like a shadow that's being created, and I have the light on here, so I don't know. Hopefully it's not too bad. So at the beginning here, they're talking about adding planar forces, okay? And when we look at adding planar forces, this first section is going to be looking at forces, and it's going to be particularly 2 or more forces that share the same application point or share a same point in space. Now, in the chapter here, they refer to forces acting on a particle, okay? All that means is we have a number of forces, 2 or more, that share the same point. And we're not taking into consideration the size, the shape, or the material of, I'm going to say, body that they are actually acting on. So we're assuming we're just dealing with a point in space or a particle. Again, it doesn't mean that the body is tiny. It just means that we're not taking into consideration all the other variables. So addition of forces in a plane mean that we're going to be all in the same plane. So we're not dealing with, if you would, a third dimension. We're just dealing with 2D or X and Y coordinates, okay? Now, as we continue to move forward here, we're going to notice that the next section talks about resultant of 2 forces. Okay, so how do we find the resultant of 2 forces? So first of all, we have to know, what does a resultant mean? So you guys tell me. You probably have come upon resultant forces before. Tell me what you know about resultants. Go ahead, Josh. Yes, it could be the combination of the X and Y forces. So when we combine them, what does that resultant represent? You can kind of go ahead, James. It's going to be represented by a vector most often. Yep, if we're dealing with forces or velocities or accelerations. But what is important about that resultant? So if I've got two forces and I create a resultant from those two forces, what is significant about that? And I'll look in the chat here. I'm going to kind of pull the chat out so that if there is anybody that wants to add anything virtually, feel free to do so, or verbally say it virtually. I'll just hear it on my computer. The amount of force on the body, yep, that is part of it. Yep, it's going to be the amount of force. But what I'm trying to get at is one particular word. So if I have two forces and I make them into one, what did I hear? It's going to have direction. Yep, to fully define a vector, we're going to have magnitude and direction. James. The sum of two forces, yep, but it's going to do something. So if I have okay, this is, maybe I'll put this a little differently because it's kind of like fill in the blank right now. You're trying to read my mind. So if I have a force that's going up and to the right, and I want to know what the resultant is, what direction is that resultant going to go? Huh? Which way? So if I've got a vertical force going directly up and I've got a horizontal force going to the right, and I want to find the resultant of those two forces, what's going to be the direction of that resultant? It's going to be diagonal, going which way? Up and to the right or down and to the left? Up and to the right, right? Because it's going to have the same net effect on the body as those other two. So a resultant is exactly that. We want to replace however many forces are on the body currently with one force that is going to have the same net effect. Okay, so it's kind of like simplifying the problem. That's what a resultant does. Okay, and you probably are like, yeah, that's what I meant. But I wanted to make sure we understood that it has the same net effect on the body as the individual forces when they're acting on it. Okay, so finding resultants is going to be one of the main things that we're going to be doing here. Okay, you'll notice that they also refer to, you guys already talked about it, magnitude and direction. So when we look at forces, we represent them by vectors. A vector is going to be a line with an arrowhead, okay? A vector is a line with an arrowhead. I'm going to say it one more time because this is really important. It's a line with an arrowhead. It is not just a line, okay? A vector is important because that arrowhead gives us direction, okay? Now, to fully define a vector, we have to have both magnitude and direction. Now, as we look right here at this vector, this is a 10-pound force. It's pointed up and to the right. When I look at exactly how this is drawn, what's the magnitude of this force? Magnitude. And I'll watch the chat box too. What's the magnitude of this force right here? Go ahead, James. It's 10 pounds. Yes. Yep. You guys got it online as well. Like it was like virtually at the same time. So 10 pounds is the magnitude. Now I can label it as 10 pounds, right? And the units are going to be the pounds. I can label it, but how else can I represent the magnitude of this vector? By how long I draw it, right? So if I have AutoCAD open, for instance, and I draw this to scale, meaning exactly 30 degrees and 10 units long, okay, I would represent that magnitude by the length. So whether it is actually identifying the units, the 10 pounds there, and maybe you sketch the vector, or if you're drawing it to scale, that length is also going to represent the magnitude, okay? And as we said, the other thing that we need to know is going to be the direction. So there's two elements here that give us direction. And what are those on this vector? There's two things that define the direction here for us. Right here, the arrowhead itself, correct. So every vector needs an arrowhead, absolutely, because that gives us direction. What's the other thing that gives us direction? The what? Exactly. So the 30 degrees tells us from the horizontal, it's up 30 degrees, right? It's rotated 30 degrees. So yes, so the 30 degrees and the arrowhead give us direction. So to fully define a vector, magnitude, 10 pounds in this case, and or the length of that vector. And then you're going to notice that direction is going to be the arrowhead and the angle. So it's really important. I can't emphasize this enough. You have to have arrowheads, and I'm very picky about that. I look at each and every one of your examples. If anybody did the practice problems in Module 1, if you even forgot one set of arrowheads, I called you out on it. I showed you. Don't forget those, all right? It's important, all right? Because we're going to be working with forces the entire time. So just really pay attention to that. Now, the other thing you're going to notice here as we look at some of the terms, they talk about line of action and sense. So your line of action is going to be the line of infinity for which we can place that force. Okay, so whether it's, continuing as it's going up and to the right or down and to the left, that's the line of action. Okay. And then the sense is going to be where you put the arrowhead on it. So if you're saying that the arrowhead is going up and to the right, the sense is going to be up and to the right. Okay. If it's going down and to the left, if the arrowhead is here, then the sense of this is down and to the left. Okay. I believe those are two concepts that you're going to come across in the Connect. I know I kind of checked those too, okay, to make sure that you would get that. All right. So vectors. Before we go into adding vectors, what are some other quantities that are represented by vectors that you've come across? Force is one of them, right? So we've got force here. We're going to be seeing that a lot in statics and throughout mechanical design. What else? Velocity. Velocity. Yep. Velocity is a vector. Tell me how velocity and speed are different. Do you remember? Velocity has a direction. Velocity becomes the vector. Speed is what? It's a scalar quantity. When you're trying to figure out what speed is, you just, if you would in your car, you just look at your speedometer. How fast am I going? But if I start wanting to know in what direction am I going north, south, east, west? Now all of a sudden I'm a vector quantity and it's velocity. Yep. Excellent. Any others? Is acceleration a vector? Yeah, it is. Yeah, it is. When acceleration is pointing in the direction of velocity, that means that you're speeding up. Remember? And when it's pointing in the opposite direction of velocity, you're slowing down. Exactly. So acceleration is a vector quantity. Momentum is another vector quantity, and it's a vector quantity because it's mass times velocity, right? So velocity is in there and now it becomes a vector. Yes. Is mass one? What do you think? It is scalar. Why is it scalar? There is a reason, and that's a great question. Mass doesn't have direction because mass is just the physical makeup of something, right? It's like what it actually is. When does it become a vector? When you do what? When you add, not velocity, when you multiply mass by, starts with a G. Gravity. Yep, you got it. When we multiply by gravity, when we multiply gravity and mass together, what do we get? Weight. Weight now is a force, and now that's going to be when it becomes a vector. Yeah. So great question. I'm glad you asked that. All right. Any others vector-wise? Okay. Despicable Me. Vector, the villain. He has both magnitude and direction. It's the best. I love that. See, when that was one I could sit down and watch with my kids, I'm like, oh yeah, that's good. Love it. Okay. Over on the right-hand side here. Over on the right-hand side. Now we're going to start looking at forces applied, in this case, to a particle or a point. Okay. So you may hear this a couple different ways. We have two forces here, P and Q, and they are acting on point A. Now, that's the particle that they're talking about, but it also can be referred to as what we call a concurrent force system. A concurrent force system means that they share a point of application, okay? And in this case, it's point A, all right? So the forces that we're going to be dealing here with in chapter 2 are going to be number 1, in a single plane, okay? And number 2, they're going to share a point. A little bit later, we'll talk about 3-dimensional forces, but right now we're going to kind of keep it simple, okay? Now, to find the resultant or the net effect of those two forces on point A. So we want to find the one force, the resultant, that would replace those two and have the same net effect. There are a couple different ways we can do that. The first way is what we call a graphical method. And the graphical method that we're seeing here is the parallelogram method, okay? So the parallelogram method, even though you see it here, I think it's good to kind of, show it and show the process. So if I want to draw this, actually, I'm going to do this. I'm going to do it on not lined paper. It'll be easier to see. This over here. Okay. One more. So I'm going to start with point A here. And I'm going to sketch P going up and to the right. Here's P. And then I'm going to sketch Q. It's going up and to the right as well, but not as steep. Okay, here's Q. And I want to find the one force that replaces that, but has the same net effect on the body. So what I'm going to do is through the endpoint of each one of these vectors, I am going to draw a construction line that's going to be parallel to the other vector. So since I've got Q here, okay, on the endpoints of P, I'm going to draw a line. I'm going to draw a construction line parallel to Q. So I'm going to try to do this as good as I can. That looks pretty parallel, okay? And now I'm going to do the same thing on the endpoints of Q. I'm going to draw a construction line parallel to P. So this one's going to go pretty parallel. And I'm going to extend those until I find an intersection, okay? Once I find that intersection, I am then going to start back at point A with the tail of my resultants vector, and I'm going to put my tip, my arrowhead, to the intersection that I just created, okay? And then I would call this R for my resultant. Now, if I was drawing this to scale, so this is a graphical method, my expectation I was be drawing this to scale. Now I can do this in a couple different ways. I could get a protractor out with a scale and draw it, however many units long we would know P and Q to be at the angles that would be identified. Now they kept this quite generic. They really didn't give us all those details. They're really just kind of showing us process right now, okay? And when I would do that, and I would do my construction lines through the end points of each one of those, and I would draw my vector here to find the magnitude, I would simply measure it and then compare it to the scale, and then I would have my magnitude of my resultant. Okay, that's using a protractor. What's another way that I could get an even more accurate result graphically? AutoCAD, absolutely. We could draw these like spot on to the, 13th decimal place accuracy, and we would be getting really accurate results. So graphically, we have some tools that we can get these results really accurately. But we also have math, and we're going to be talking about, how we can solve this with math as well, okay? So this method right here is called the parallelogram method. Parallelogram. I'm trying to sound it out as I'm writing. Parallelogram method. And this is considered a graphical method to solve for a resultant when there are two forces present, okay? Now there's another graphical method that we can use, and it's called the triangle method. And again, both of these, parallelogram method and triangle method, will be when we only have two forces that we're trying to find the resultant for, okay? So the other way that we're going to do this, we're going to start with A, and this is going to be called the triangle method. Okay. And I'm going to start here at A. And I'm going to pick one of those two forces to draw. Okay. And it doesn't matter which one, because no matter which way we start or what order we add these in, we're going to end up with the same result. So I'm going to start first with Q, just because it's right here. So I'm going to draw it about the same as I did last time. So this is Q. And on the endpoint of Q, I'm going to draw P. Okay. Right. And now what I've done is I've added these two vectors together. So this would be Q plus P. And then if I want to find the result, I'm going to say equal to the resultant. And I'm going to go just like I did before. I'm going to start my tail at point A, the point of application. And I'm going to put my tip at the tip of that last vector in that triangle. So see how we have two sides of a triangle. Okay, and it created a triangle. Now, in this case, I added them in a certain order, and I can actually write a vector equation that would represent that. Okay, and that would be Q plus P is equal to R. Okay, now The key here is that I said vector equation. This is not an algebraic equation. So if Q is 40 units long and P is 60 units long, as you look here, will R, the resultant, be 100 units long? No, it's not an algebraic addition. It is a vector addition. So we need to differentiate it. And there's one of two ways that you'll see it happen. You can either put a vector symbol above each one of the variables, or in the operator, you can say Q plus with a greater than sign. This says that it's a vector addition, plus P is equal to R, okay? One of those two ways you need to show it. Most often you'll see me, if we're gonna write, the equations, I'll do it with the little symbol above, okay? Now, if I were to change the order here, if I would actually start with P and then add Q, the order of my vector addition then would just change to P plus vectorially Q is equal to R. But I would end up with the very same resultant. So you can add vectors in any order if you're finding the resultant, and your resultant will still be the same. Okay, this is called the triangle method because there's two forces that we're adding, and then the resultant kind of makes that longest side. But if we have more than two, we can continue to add more forces to this. That's called the tip to tail method. And you can see why. You're going to start with your tail at your origin, and then you're going to continue to add the next vector to the tip of the previous vector. So it's called tip to tail method. Okay. All right. Questions so far? Yeah.
The greater than symbol, can you throw that either on Q or P, or does it have to be specific to the second vector that you're?
It's just the operator. So for instance, if I was adding P plus Q plus T plus Z, the operator would just have that extra greater than sign. Yep, it's the operator. No, good question. Yeah. Others. And we'll spend a little bit more time on vector equations, but just kind of an introduction and seeing the relationship here. Okay. All right. Okay, so they showed us the parallelogram method. I'm going to turn the page, page 20. Okay. Now we're going to look at vector additions, okay? Vector additions. Now, what we just did with the two forces, these were considered vector additions, all right? We added two vectors to get a resultant, okay? We can continue to add more forces. So for instance, in the case of, and I'm not crazy about their illustration, but I'm actually gonna go down to part B here. This is the best one, all right? Here they introduced a third force. They've got P plus Q, and then they added S. Do you see that? So this is that tip to tail method that we were talking about earlier. And then the resultant is going to start back at the origin, and it is then going to go to the tip of the very last vector. So graphically, this is the tip to tail method. Okay, graphically, this is the tip to tail method. We are not going to be focusing so much on the graphical method. I want you to just be able to sketch it and identify it, because then you're going to be using those sketches to, solve them with, algebra and trig, right? Okay. So that's the tip to tail method. Page 22. So we are ready to start looking at sample problem 2.1. Sample problem 2.1, if you look at our practice problems, okay, this is going to be the first practice problem that we're going to do. So what you're going to want to do is get out a piece of paper and kind of start off our practice problems so that you can later hand those in, okay? Now, remember, you don't have to put on here Module 2 practice problems or your name, because you'll be handing in it and I'll know exactly who it is. But you are going to want to tell me that this is sample problem 2.1. And this happens to be on page 23. Okay. So the sample problem that we have here, I'm gonna kind of scooch this over. It says that we have two forces, P and Q, and they act on a bolt, A. We want to determine what their resultant is. Now, what they've done is they've done this a couple different ways. We're gonna look at it first graphically using the parallelogram method and the triangle method. And then we're gonna solve it using the cosine and the sine laws, okay? So let's do the graphical method first, and this is gonna be sketching, okay? And my expectation with sketching is that you're sketching relatively straight lines, or if you know you're not great at that, you don't have to scale them or make them perfect, but if you think that you probably need a straight edge, then maybe get out a straight edge, okay? But if you can, you know, sketch pretty decently and relatively straight, then, and we can make good labels, that'll be fine. So I'm going to start with the graphical solution first. And the first one we're going to do is the parallelogram method. Okay. Now, the parallelogram method, we are going to create a sketch that is going to represent what we see there. Now, we don't need to draw the bolt A, but what we want to do is we want to identify an origin. And then we're going to label it point A. And then what we're going to do is we are going to draw each one of those vectors. So they actually, you know, it's not exactly, we used the letters P and Q earlier, but Q is actually the one this time that's on top, if you would, and it's 60 newtons long, and P is going to be 40 newtons long. You'll also notice that the angles that they're at are P is 20 degrees from horizontal, and then Q is 25 degrees between, so that would be 45 degrees, if you would, from horizontal. Now, what you want to do is you don't have to make these perfect, but you do want to make them proportional as you're drawing your sketches, okay? You want to have a good representation of it. So as we're looking here, we're going to draw Q, be about this long, 45 degrees-ish, right, from what would be our horizontal axis. Here's X, here would be a Y. And this would be our force Q. Now, if you wanted to put the 60 newtons on there, we don't really need it for this graphical solution, but just kind of knowing that that's 60 newtons, then when I draw my P in place, I'm going to definitely want to make it shorter because P is only 40 newtons long, right? And this is going to be my P. Now, using that parallelogram method, what we want to do now is we want to draw through the endpoint of each one of those forces at the tip where the arrowhead is, a line parallel to the other force. So on the endpoints of Q here, I want to draw a line through there, sketch a line, whether it's dotted or very light. I want to make a line, a construction line that's going to be parallel to P, kind of parallel. And then through the endpoint of P, I want to draw a line parallel to Q. Oh, that's not parallel at all. That's why we have pencils. Go this way. That looks better. Okay. And we want to find an intersection. Now, once we find that intersection, we're going to start the tail of our resultant at point A, point of application, and we're going to draw its tip to the intersection of those two construction lines that we just created, okay? And then this would be labeled our resultant, okay? Now, each one of these forces needs an arrowhead. Remember, these are all three vectors. And then because we're trying to find the resultant, we also want to label the angle that it's creating. In this case, they're labeling it from the horizontal. You want to measure from a known axis. It could be the y-axis or it could be the x-axis, and they're calling this alpha or A. Okay. Now, as you can imagine, using AutoCAD would be a great resource where you can actually measure all of these things, create dimensions, and you'd have really nice, accurate results, okay? You're not going to be required to do that. All I want you to do is make some good sketches of the process to find the resultant as we see here, okay? Now, the other way that we can do it is that triangle method, okay? The triangle method. So, and they're showing this as an example right here. So here's first the parallelogram method, and now here's going to be the triangle method. They're adding these vectors with P first and then Q. So let's draw out the very same thing where we're going to start with our point A. We'll have an x-axis. We'll have a y-axis. Now, depending how close you get these, you should end up with a resultant that's going to be the very same value. So if we would be drawing this in AutoCAD and we would do the parallelogram method first and then the triangle method, your resultant will come out exactly the same. Okay, but we're going to sketch this one. So this one, we're going to start with force P. Okay. And on the endpoint of P, I'm now going to draw Q. So Q, remember, was at a 45-degree angle. So a little bit taller or a little bit, more of an angle, if you would, and longer, steeper, maybe is that what I want to say? And then that's the endpoint of Q. Now our resultant, its tail is going to start back at the application point, which is A, and its tip is going to go to the tip of the last vector. So this is going to be our resultant. And then to get its angle, this would be alpha. So as we compare these two, you're going to notice that our resultant, I didn't do too bad. They're about the same length, and it looks like pretty close on the angle itself. So now, so both of them will give you the very same result. Okay. Questions? Okay, let's look at now solving these with the information that we know, but then actually getting the numbers for them. So the third way that we're going to look at this is going to be the trig method. So all I'm going to do is I'm going to go on the back side here, and I'm going to redraw my diagram only because I'm going to add some notes here. You don't have to redraw yours. If yours is big enough to kind of add some stuff to it, I just want to do the rest of the problem, but I want to have the whole piece of paper here available to me. So I'm going to do my B, or I'm sorry, my Q. I think this one's, oh no, this is P, and then Q. And then my resultant. I didn't hit that very good. A little less. They're meeting at that point right there. And this is R. Now from horizontal, this is P. I know this angle right here is 20 degrees. And I also know that from horizontal, I guess I drew this a little steep. This is 45 degrees, right? From my original diagram, because right here, this was 20 degrees from horizontal and then another 25. So to Q is actually 45. Okay. Now, if we actually put this in the greatest spot, if we kind of extend this out right here, so this is I'll put this as 20 degrees, but then this angle right here is the 25. So we want to kind of recognize that. Okay. Now we want to find out what is the magnitude of our resultant when we know that Q is equal to 60 newtons and P is equal to 40 newtons. So we know the magnitude of P and Q. And as we look at this triangle here, so here is our triangle, right? Here's our triangle. Are there any angles within the inside of that triangle that we could find?
You could find the angle between Q and 25.
We can do this angle right here, right?
Yeah, it'd be 25 minus 180.
Exactly. So this line, if we extend this right here, this is going to be like, 180 degrees from line to line, right? But then if we subtract off 25, we're going to get this angle. So I'm going to call this angle beta, okay? So beta is going to be equal to 180 degrees minus 25 degrees. So our beta is that 155, right? Yeah, so beta is 155 degrees, right? Now, as we look here, if I know this angle, right? And I know the magnitude of each of the sides, and I'm trying to find the magnitude of the side opposite of beta, is there a trig function that you know of that can help us? The law of cosines, exactly. A lot of times, you know, we usually want to try the law of sines because that one's a little bit easier one, but unfortunately, we don't know these two angles, do we? We have too many unknowns for the law of sine. So the law of cosines is the one that we want to use. So write out the law of cosines for me using what we have here, our P's, our Q's, our R's, and our angle. Go ahead and write it out before we go too far. I want to see if you kind of remember. If you don't remember, it's okay. I'm gonna do it in just a second. So yeah, we want to use our cosine law. So you should come up with the side opposite the angle, which is our R. This is going to be our R squared. It's going to be equal to one of the sides squared, so I'm going to say P squared, plus the other side squared, Q squared, minus 2 times P times Q times the cosine of what we called beta. Does that look familiar? No, it doesn't look familiar at all. You guys are taking calculus. It should be pretty familiar. Or you should be like, yeah, I think I've seen that before. Okay. Now let's look at what we know. We know the magnitude of P, right? We know it to be 40. We know the magnitude of Q. We know it to be 60. We know the magnitude of beta. So our only unknown is our R, right? Our resultant. So now to solve for this resultant, we are going to say R is equal to, and we're going to do the square root, and we're going to put all of our quantities underneath here, okay? So we're going to start with P. P is 40 newtons squared. Make sure that you put the units in all phases of the problem. That's something I'm going to require you to do all the way along here. So start putting it in there. So don't put 40 squared, it's 40 newtons squared. Plus Q, 60 newtons squared. Minus 2 times 40 newtons times 60 newtons. Yep, you're going to write it in every place. Times the cosine of 155 degrees. Okay. All right. So go ahead and solve this. Now, what I'm going to do is I'm going to kind of break it into chunks so you can compare the chunks if you need to, but go ahead and punch it in your calculator. The final answer you can compare. It's right here in our example problem. You're supposed to get 97.7 newtons. That's why we're doing the sample problems, to make sure that that you can get the same answer. Now, if you're not getting the 97.73, It's probably because of a negative sign. If you do the cosine of 155, you should get a negative 0.9063. And if you do, there's a negative out front here, so that sign becomes positive underneath the radical. So you're adding that last portion of the equation, okay? That's usually something that trips people up, where they actually subtract this off and you need to add it. And now these are the newtons squared. So you would just add 1600 plus 3600 plus 4350.27 under the radical, and then take the square root. And when you do that, you're going to also take the square root of the newtons, so it becomes, or the newtons squared, so it becomes newtons for the final units. So how are we doing? Any questions on that? How about virtually? Are you guys doing okay? Did you get the 97.73? Yeah.
Yep, that's what I got.
Awesome, Chris. Thank you. Let me know if you're not. I want to make sure, I don't want to go too far. Make sure I give you a chance to punch it in your calculator a time or two. All good here. Thank you, Jason. Yeah, this is a great, and that's why sample problems are so important, and that I want you guys to get this experience, because that way you can practice on your calculator, like how to punch it in again. Jack has a thumbs up. Awesome. Good. And the key to this one is you got that negative 0.9063 for the cosine of 155. And then when you multiply it here, Christian, good. Then a negative times a negative becomes a positive. All right, cool. Cool. We ready to move forward and find then? We've got to find an angle yet. All right. So now that we have the magnitude of our resultant right here, we now need to know, we know it's going up and to the right, so we've got our arrowhead on there, but we need to know, what the actual angle is from horizontal, okay? So they wanted to know, what is this angle right here, okay? So this angle from the resultant to our horizontal, they call that alpha, okay? They call that alpha. Now, we know there's a part of alpha. We know 20 degrees is here, right? But we need to know what is this angle right here, right? Now that we know the magnitude of that resultant, and we know the magnitude of P, and we know the magnitude of Q, and we know 155, can we find this angle? What do we want to call this one? We'll call this one theta. We can find theta. And alpha is going to be theta plus 20 degrees, right? So remember, this is our triangle. This is an internal angle. Is there a way we could find theta? Anyone? Go ahead, Christian.
Alpha minus 20 degrees.
Right, but we don't know what alpha is
Log
unless we
signs.
get theta. Do you see that? We need theta first. So alpha is going to be theta plus, and theta is the internal angle here. So let me do this. I'm going to grab a colors because I don't think it's that easy to see. So here is my triangle.
We could set theta equal to was that adjacent over hypotenuse?
No, we can't, because this is not a right
Oh,
triangle.
wait,
Those
yeah.
aren't, we're not
law
eligible
of
for those
sines.
right now. But what I heard it, I think,
Law of sines.
the law of sines, we can use it. Okay, so let's see. So on the law of sines, we need to have a side and an opposite angle, right? So we know the resultant is equal to 97.73, right? So this is known now. This is 97.73 newtons. And we know the side or the angle opposite of it is 155. So we would say, all right, that magnitude and those two are a pair. Those are known. And then we know what the value of Q is. We know this value to be 60 newtons and it's opposite of theta, right? So our only unknown here is the theta. So what we're going to do is we're going to use the sine law. And we're going to say, all right, the sine of theta, we're going to put that one on top over what it's opposite to, which is going to be Q, 60 newtons. It's going to be equal to, And now we're gonna use on this one, on the top, we're gonna put the angle. It's gonna be the sine of 155 over the side that it's opposite. Oops, I did this wrong, sorry. I was pointing to the right place. Sine 155 on top over 97.73 newtons. There we go. That's our setup. So our only unknown here is the theta. So we're going to multiply 60 newtons on the opposite side here. Okay. So sine theta is going to be equal to, and if you take sine 155 times 60 divided by 97.73, the newtons cancel out. So make sure you show your units canceled. And we're going to get 0.2595. And then you're going to use your, depending on your calculator, it might be the A sign or the A sign or the second function sign or the sign to the -1. And your theta is going to be equal to 15.04 degrees. Okay. Do you guys get those numbers? But that's only part of our problem, right? We need alpha. We need the angle of that resultant to the x-axis or the horizontal. So now that we have theta, 15.04 degrees, we can simply add it to 20, and then we can calculate our alpha, right? So our alpha is going to be equal to 15.04 degrees plus 20 degrees. So alpha is going to be equal to 35.04 degrees. Down just a little bit there. Did everybody get the 35.04? Yeah. Yeah. Okay. Virtually, how did you guys do? Any questions at all? All right. So graphically, and I call this analytically or by trig, okay? We're using this line, in this case, the law of cosines and the sine law to solve for sides and angles, okay? So an application of some of the math that you've had in the past. All right, cool. All right, so put this one on the side, make sure that you keep track of it because it'll be part of what you hand in for your practice problems, right? Let's do another sample problem, okay? Our next sample problem is going to be sample problem 2.2. It's on the bottom here. This is another one that's in our practice problem packet. So our illustration here, we have two tugboats that are pulling a barge. If the resultant of the forces exerted by the tugboats is 5,000 pounds directed along the axis of the barge. So the axis of the barge is right here. It's horizontal, okay? Determine the tension in each one of the ropes given alpha angle to be 45 degrees. We're only going to do part A here. We're not going to worry about part B. Okay, so we're just going to do part A. So we want to know what is the magnitude of each one of these forces if we're going to be pulling this barge to the right, okay, along here, and our resultant is going to be horizontal. Okay, so let's kind of start by drawing a representation of the forces that we see here. So this is going to be sample problem 2.2. Okay. And our point that we're pulling on is going to be point B. Okay. And we're going to draw an x-axis and a y-axis just to give us, if you would, perspective. Now, we know, and it says in our problem, that we have a 5,000 pound force is directed along the axis of the barge, which is horizontal, okay? And since this barge, you're going to notice there's kind of these waves in the back. The assumption is that it's moving to the right, okay? And the tugboats are pulling it, and they're going up and to the right and down and to the right. So that means that our 5,000 pounds is acting on B, pulling on B, and it's being directed to the right. This is our resultant. And our resultant is 5,000 pounds. Okay. Now, I'm just going to draw a line representing the line of action of each one of those tugboats. Okay, a line of action of each one of those tugboats. The one going up to A, they're calling that 1, is going to be 30 degrees, and the one going down to C, that's number 2, that's going to be 45 degrees. So this one's going to be a little bit more shallow. So again, line of action. So I'm just drawing a construction line and then another construction line about 45 degrees. Okay. So this one is 30. This one is 45. Now, we're going to kind of do our parallelogram method backwards, if you would. So on the endpoint of our resultant, remember how the resultant always tries to find that, that intersection created? So what we're going to do is through the endpoint of the resultant, we're going to draw a line parallel to each of those construction lines that we just created. So I'm going to draw a line parallel right now through here. Okay. We're going to pretend that it's on that endpoint parallel here. And then we're going to do the same thing on this side. This one's going to be a little bit more shallow. So it's going to be something like this. Okay. So we have the resultant and we're using these construction lines then on the endpoints to find then intersections to where the tugboat tensions would be. So now we're going to start with the application point at the origin B. And our arrowheads are going to go to the intersections that we just created. And these two are going to represent the tugboat tension 1 and the tugboat tension 2. So this is your parallelogram method. Okay, just a sketch that we have here. Now, we want to find what is the tension in each one of those cables on the tugboat, right? We want to find what that is. So what I want you to do is, even though we have a parallelogram here, do you see a triangle kind of similar to what we used in the last sample problem? Do you see that there? Do you see how this side right here would represent and be equivalent to T1? Do you see that? Do you see how this line right here would be the same as T1, right? By doing that, what it allows us to do is kind of see the triangle develop and then see if we could apply the sine or the cosine law to what we have here to find the unknown T1 and T2. Okay. Now, as we look here and the construction that we have, and we look at our triangle, are there any angles that we know? We know the 45 because that one's drawn in there, you know, by the diagram. But do we know this angle or this angle? The one on the right is 30. So if we extend this out like this, this is 30, right? So thus, this is going to make this angle 30 as well. Yes. And we know the magnitude here, even though I have this here, R is equal to, I'm going to put it right here, 5,000 pounds. So this is a known length, right?
Use the C squared equals A squared plus B squared method to find the last angle.
No, you actually could find the last angle by a different method. What else could we, what is the?
That's fine.
Yeah, you're thinking of Pythagorean's theorem when we have a right triangle. We don't have a right triangle here.
All three of them together equals 180 degrees.
Oh, that's what you were thinking of, right? So we could find this last angle, right? We could find, we'll call this one theta. Theta would equal 180 minus 45 minus 30 degrees, right? So our theta should come out to be 105 degrees. Yeah, you're correct. So we can put equal to 105 degrees. But we need to find T1 and T2. So what would be an approach, a method? We could use the law of sines here, right? Because we could take 105 and 5,000. Those would be a pair. Those are both known, right? And I mean the sine of 105. And then we have the sine of 30 and T2. And then T2 would be our only unknown in that pair. And then we could do the same thing and then do 45 and T1, where T1 would be the unknown there. Absolutely. So let's go ahead and do that. So let's apply the sine law. And we'll do it first. We want to do T1 or T2 first. Any preferences? T1, sure, just because it's first, right? So we need to solve for T1. So we're going to put T1 on the top. That's a length. And opposite T1 would be sine of 45. So T1 is here. The opposite angle is 45. So we're going to put it over the sine of 45 is equal to, and now we're going to take the 5,000 pounds. That's the length of our side or the magnitude of our side. And it's going to be over the sine of 105. So 5,000 pounds over the sine of 105. So then we're going to multiply up on top here, sine of 45 degrees, extend that out. And our T1 will be equal to and make sure you add your units in all phases of the problem so you can see if you end up canceling something out, if something's left over. Now here we would not cancel out the signs. Okay, we have to actually do that work. We have to get the decimal equivalents of each. And then you should end up with 2588.2 as the magnitude of T1 or something very close. And then you want to reapply the sine of law or the law of sines or the sine law to get T2. Everybody get T1 or working on it? And then T2, we would put that over the sine of 30. And we would use that same 5,000 pounds over sine of 105. And then to solve for T2, we would multiply the sine of 30 up. And then T2, oh, I did do that wrong, you guys.
I keep looking.
Yeah, I looked at the wrong one. 3660.3. I am so sorry. Why didn't anybody tell me? Were you guys?
I was afraid I'd be wrong.
Oh, don't be afraid. I was glancing at it and I'm glancing at my finished product and I actually solved for T2 first instead of T1. We did it in opposite order. So T2 is 2588.2 pounds. Just keeping you on your toes. No, that wasn't intentional. I was glancing over and I thought I did T1 first, but it was T2. So I mixed them up. Yeah, don't be afraid. That's why we do them together and I'm not perfect. So we're doing these as we're doing these together as we go along. Okay. So for this problem, you want to make sure that you have a nice diagram, okay, kind of showing that sketch of the graphical solution. And then what you're going to do is you're going to identify your knowns, your unknowns, and then you're going to solve for any unknowns. In this case, we need to find T1 and T2. So you better show where T1 and T2 are here. These are forces. You need arrowheads on everything. And then you're going to solve for them using the sine law for each one, and then making sure that you have your units in all phases of the problem, including the final answer. Okay. Any questions at all? Okay, we got it. All right. So let's go back to problem here. So we just looked at sample problem 2.2. And then you're going to notice on the next page, page 25, we use that triangle, same one as they did, and then using the law of sines or the sine law to calculate for T1 and T2, and then those answers are down here as well. Okay. All right, and then we're not going to worry about part B. Worry about part. So I'm trying to get this out of the way here. Now, as we look at these problems here, you're going to notice that we're up on our next page, which is page 26. This is the problem section for which I picked our application problems from. So if we look at our application problems, so many pieces of paper here. Hold on. What am I doing? Here they are. So if we look at our application problems, and if you're in the room and you want to, they're in the front here, or if you go on module 2 and the application problems, the first 3 here, you would be ready to get started on those. Okay, so 2.1, 2.5, and 2.7, and those are going to be found on pages 26 and 27. So as long as we're here and the information is kind of fresh, why don't we take a peek at those and see if we have any questions. So we're going to take a look at number 2.1. Now for number 2.1, it says that you want to determine, the book says graphically, I'm telling you analytically, okay? Meaning you want to do the trig, cosine or the sine law and or combination of, and you want to find the magnitude and direction of the resultant of the two forces that are acting. So 2.1 is right here, okay? And so you want to solve it in that very same way that we just did the last 2 problems. So you're going to draw me a nice diagram, and you can show the parallelogram method or the triangle method to show how you would, get your triangle for these 2 forces. So the orientation and everything is very similar to what we saw in that very first problem. So the process for doing that would be identical here. So you'd want to find the resultant of those 2 forces. And then you would show the diagram, sketching the graphical method, but then all of your labels and solving it using the law of cosines and the law of sines. So any questions on this one? That's 2.1. Let's look at 2.5. 2.5 is directly below. Okay. This one says we have a steel tank. It's positioned. Knowing that alpha is equal to 20 degrees determined by trigonometry, the required magnitude of force P, if the resultant of the 2 forces applied at A is to be vertical. So vertical is going to be just like this. This is just like the sample problem that we just did with the barge, except the barge was oriented horizontally. Okay. This one is oriented vertically. So the process will be exactly the same as sample problem 2.2, okay? And then labels and all that kind of stuff would be exactly the same type of format. And then the third problem that you would be ready for in this set would be on page 27, and it is 2.7 at the top here. We have a trolley that moves along a horizontal beam, is acted on by 2 forces. Knowing that alpha is 25, determined by trigonometry, the magnitude of force P, so that the resultant exerted on that trolley is vertical. Okay, right down here. And then you also want to find the corresponding magnitude of the resultant. So that one's kind of a combination of the 2 that we looked at, not really exactly like either one of the example problems. Okay, so as we look at those 3, does anybody want any guidance or direction, or like, no, I got it. I think I could, decipher that. And I don't want anybody to think that if you're like, no, I kind of want to see it, just let me know. So virtually, if anybody wants to see it, say what number you want to see. I've got 3 of them here, and we have a little bit of time. We can get started on these application problems. Go ahead, James. What are you thinking? Did you want to see any of them? So we've got 2.1 on the table, 2.5, and 2.7. So 2.1, 2.5, and 2.7. If not, that's totally fine. If you want to work on them independently, and then we just keep going. No news is good news to me. So I don't want it to be like I'm totally confused. I don't even want to ask. Or you're like, yeah, I got it. No problem. I'm gonna always assume I got it, no problem. I don't hear anything. Okay. So it doesn't seem like, and I don't like wasting anybody's time. If you guys feel confident in that process and how it's done, then we're just gonna move on. Okay. So as I'm looking at the times, we've been talking for about an hour and 20 minutes, and this is actually a pretty good breaking point. So what we're gonna do is when we get back, we'll continue on in the chapter and do a couple more practice problems and then look at more application problems. So I'm gonna stop the recording right here.